Hello, BC Calculus students. This is Mr. Johnson, and this is section 1.5, which is going to be on exponential functions. So first of all, what is an exponential function? Well, our first thought is probably e to the x, which is one of the most common functions that we have, this exponential function that we use in calculus. More generically, we might have just y equals a to the x. So we could have like 2 to the x or 3 to the x or e to the x or whatever the case is. A typical graph is going to look like this. Obviously, there could be a number of transformations on this type of graph. With this graph, there is an important point here, which is going to be 0, 1. And again, there could be transformations, but if there is a sort of a basic exponential function, 0, 1 is going to be sort of our main point that we're going to analyze because e to the 0 is 1, 2 to the 0 is 1, 4 to the 0 is 1, and so on. The domain is going to be from negative infinity to infinity, and then often the range is 0 to infinity. If we look at, for instance, a to the x, negative a to the x, and a to the negative x, we can see the different types of transformations that occur. So this would be just an example of a to the x, which again, e to the x, 2 to the x, 3 to the x, those all fit in that category. Negative a to the x means that vertically we're going to reflect over the x-axis. So we're going to get a graph that looks something like this. And then if we have a to the negative x, it's going to be a horizontal reflection over the y-axis, so then we'll get a graph that looks like this. And then e to the x, that's going to fit into the category of that red one. Again, it's going to be similar to 2 to the x or 3 to the x and so on. All right, because we're talking about e to the x, this is sort of off topic slightly. We're going to talk about limits more specifically in chapter 2, but the one of the sort of standard limit definitions of e is the limit as x goes to infinity of the quantity 1 plus 1 divided by x to the power of x. And there are other definitions of e. We'll talk a lot more about these as we get into chapter 2, but sort of just as a side note here, that's the limit definition of e. All right, some laws of exponents. So in this case, if you have a to the x times a to the y, you have a to the power of x plus y. A to the x to the y is a power to a power, and so you multiply the powers. A to the x divided by a to the y, you subtract the powers, and then you can distribute the powers, in this case, a to the x and b to the x. All right, we're going to go on to the next page. Okay, here we're going to talk about a simple application. This is the Pert formula, which you've seen probably since Algebra 2, I'm guessing. A equals P times E to the RT. That's the Pert that you get there, so it's a lot of different applications there. We're going to talk about half-life. So the way we're going to use this is we're going to say that the amount is going to be half of the starting amount, and that occurs after 700 years. So what we're going to first find is what rate we're dealing with in this particular case. Now we can cancel a p on both sides, so it doesn't matter what that starting is. And then we have e to the power of 700 times r. Now again, logarithms exist in order to calculate exponential variables. And so in this case, we're going to turn this into an exponential, or excuse me, a logarithmic equation. So we have the natural log of 1/2, which is equal to 700 times r. So we've accessed the exponent through this logarithm, and then we just divide by 700, and we have our value of r. And I'll just leave it kind of general like that for right now. Okay, so then what we're going to do is we're going to take 10 grams initially, and we want to calculate how much would be left over after 300 years. So we have our amount that we're trying to calculate. We have our initial 10. We have E, and then now we have the R value of the natural log of 1/2 divided by 700, and we're going to multiply that by 300, and all of that's in the exponent. And so then if you, excuse me, if you do this in your calculator and you round to 3 decimal places, you get 7.430. Keep in mind with our, with AP calculus, you can also take 7.429. You don't have to round that third decimal place. That would be acceptable as an answer as well. All right, let's talk about solving this equation. Now this one, we're going to do algebraically. If you were to graph this on your calculator, it's very difficult to get a nice window where these two equations will cross. And the main reason is that e to the x just increases so dramatically. And so if you were to graph e to the x, you know that it looks like that general a to the x graph that I was talking about. So it looks like this. And we know that 1 million would just be y equals 1 million, which is some sort of horizontal line. Now, on your calculator, if you were trying to tweak your window and change your window, that could be a little bit cumbersome, just again because of the size of the number. And so if we think about this algebraically, we're looking for when this these two graphs intersect, what this point of intersection is. And so we're essentially looking at e to the x greater than 1 million. And if we were to use logarithms, so if we were to take the natural log of both sides, okay, the natural log of e to the x is simply just x, and so the natural log of 1 million would be our final answer there. So x greater than that is what we're looking for, and that's just a simple algebraic solution versus having to go after it on the calculator. All right, let's do our last example here. We're just going to graph this without a calculator, and we're going to go through the different transformations. So first off, if we have e to the x, it looks something like this. E to the negative x means that we're going to reflect, I was showing you this at the very beginning here, so we're going to reflect it over the y-axis. We're going to reflect it horizontally, so it's going to look something like that. We're just doing a sketch here, so don't be too concerned about the scale necessarily. I'm just assuming that that one box is just one. Then we're going to shrink it vertically, so by 1/2, which means that now we are going to it's going to be sort of like this, and that would be y equals 1/2 e to the negative x, and then we'll move all of that down 1 unit. And so we're going to get a final answer that looks something like that. There will be a horizontal asymptote there at y equals -1, so keep that in mind. But then this is going to be our final answer here in black is our graph there. Okay, so that is a quick little section there. That is section 1.5. Thanks.